Okay, let's see what I can tell you about elements. Again, you recognize our system, which have been modified again a little bit by this cantilever beam here. Yeah, let's go to the curation mode and to the nodal mode, yeah, which is the most general one. Then we can take a look at the element properties by looking at the element context menu. We can just open it by double-clicking the element. And again, you see several tabs. Here we have the context menu, the context tab with some general things. Most important is that one here, which we just, if we just tick it, we can make visible the element, local element coordinate system. So with these elemental coordinates here in X, the local element axis X running from the first node to the second node, just in the sequence how we have defined this element, while Y and Z, you see it better here, are just coordinates perpendicular to X, just spanning the cross section. They are automatically generated, but we can modify them. We will see that in a second. Let's go to props. Here you see all the stiffnesses, bending stiffnesses, longitudinal stiffness, and here the torsional stiffness. We can also give in load, constant line loads in the element in local orientation or in global one. If we tick global, it will be oriented in global directions. And here GE means Grundelement in German, the basic element. We will see that in a second what that means. Yeah, then you see here ticked here, that means that the properties of element 1 will be taken as the standard for every new element. If we go to element number 2, you see it's not the standard. So that means if I will generate a new element, it will just receive automatically these properties here of the standard, which is in this case element number 1. Then we come to the local system. That refers exactly to this local element system. And you see we have three angles, which are the angles relatively between the global coordinates, these are these here, or here these, and the orientation of the local x-axis. So we have the phi angle, which is the elevation angle from the xy plane. So this is parallel to the xy plane, that means phi is 0. So that one is perpendicular to phi, that means here we will have an angle of 2. Let's go to this element here, now, of 90 degrees. You see here this element, there we have a phi of 90 degrees, that means the elevation plus 90 in that direction, minus 90 downward. Then you see this, this cantilever, which is just rotated by 90 degrees around the global z-axis. Here you see we have the related azimuth angle theta to be 90 degrees. That means relatively to the global coordinate, x-coordinate, rotating around the z-axis, the global one in positive direction, that's the positive rotation angle theta. That explains the orientation of the local system in this highlighted element. Let's go back to element number 1. And if you would now like to rotate the element system around the local x-axis, that's exactly this angle rho, about the torsion of this local coordinate system. If I just give 30 degrees, you will see how the local y and z axis are now rotated along the x-axis. By that, we are able just to adjust the local element system rho by the angle rho. And that is insofar important. If I just go back to the previous sheet here for properties, you see we have only bending stiffnesses with the moment of inertia as Iy and Iz. That means that we just assume that we have only main axis cross sections and their orientations. That's something what you have to make sure, if we just generate the input, that we always have to adapt the local element systems with respect to the main cross section values which we can give in here. Okay, going back to Loxis, going further to the next tab here with the load. Yeah, and more or less self-explain. We can give in a number for self-weight. Self-weight, where we just assume that the self-weight is just acting in direction of Z. The Z should be the axis of gravity, positive downward typically, so indicating that literally that is the floor, and the self-weight is going downward. Snow load, I just put off the self-weight. Snow load, of course, is just also acting in a gravity direction, and you see if I just maximize that, that is clearly indicated that that must be snow here. So again, going to the element context menu, we can also give in pre-stress, which is something what we can't see here, the pre-stress, and we can also give in some wind pressure. The wind pressure, there we have also some assumption. The wind pressure, there we assume that the wind pressure is always going in parallel to the XY plane. Perhaps I just minimize that again, then we can see it better. So we minimize it again. So we simply assume that the wind is just flowing parallel to the XY plane. And that's exactly what we can give in. So for instance, for the column, there's something where we can see it. So the wind pressure, and we can just say, okay, in which direction the wind is blowing. So the wind blowing, in this case, we assume that it's just blowing in the direction 1 in X and Y direction, and then it looks like this, the intensity of the wind to the column. Horizontally parallel to the XY plane, that's our assumption. And if we just look from above, look from above, there you see how nicely the wind is now blowing in the direction x equal to 1 and y equal to 1. Here in these two graphs, you just see the projection into the respective planes. Now, let's turn it back. Here we are. These are the loads. Perhaps some other comment with respect to self-weight and snow. If I just incline this a little bit, and let's take away the wind here from this element. And if we apply load, then you see that the snow was always defined with respect to the projection of this element into the XY plane, while the self-weight of course is defined with respect to the true length, not to the projected. So we can really nicely distinguish between these different kind of load scenario. In contrast to that, I'll just take it away. That's what we call element loads. Element loads, we can go to the context and to the properties. So we can also give in some loads, line loads, for instance QZ, which are defined now in local orientation. The local orientation, if we just set on the local system, so you see the local Z direction is perpendicular to the element, and by that this line load is acting in this local direction. We can switch to global, and then all in a sudden these loads are just acting in the global direction. So that's similar or equivalent to the definition of the self-weight. But here with that, we are able just to generate also loads locally defined with respect to the element coordinates. So you see we have all kinds of different possibilities. Line loads, constant line loads in local or global directions, and this element kind of loads with self-weight, snow load, defined with respect to the global direction of gravity and the wind pressure. These are the possibilities. I'll just take away the loads, then we can come to further definitions. So here, take away the wind. So much about the element loads. And further going on with our element context menu, we have here the tab with the theory. You see we can switch between theory of first order and eventually, if it's possible, into the force density method, which will be the subject of another tutorial. Then you see finally the related notes. means this element is just running from node 1 to node 2. The next element 2 is running from node 1 to node 4. So we can simply check what are these elements, and eventually we can also have these nodes and we can highlight them. That's ticking at these respective cells here. Okay. What remains are the drop-down menus for elements. These of course again depend on the modes where we are. So perhaps starting with the select mode, and we just go to any element with the right mouse button, pushing that, we just can open this drop-down menu here for the select mode. It's rather small. We can close again the mouse, we can edit the element, and we can make visible the element system, as we just see, or we can also make the complete element invisible if we just click at that. There you see it's gone. To make it visible again, we can do it like this, that we now go into the off of our view, press the right button and go to visible next choice, and then we just draw our rubber band across this region where we just expect those invisible elements, and they are just back again. That is nice. And let's now look into the curation mode. What is different? We just go to element, right mouse button, and you see we have some more things like splitting, merging, blending and things like that. These two we just have seen, and now it's also possible to delete an element. So if we choose delete, we have two options. We put it to trash. That means we can just recover it from the trash. And also we can choose the other option which says revocably. That means we can delete it and just get it back once from trash. Well, everything, if you put it to trash, let's do this. So you see we have now one thing just put into the trash. If we just take another element and also we put it into the trash, delete it, put it to trash. So now you see we have two items into the trash, and we can now get these back, the second element from the trash, the first element from the trash. So by that we can just have some safety in just working with elements, deleting and all these things. By the way, these delete options are also valid for nodes. Okay, recoverably means simply, if we just delete something, revocably, we can make it back here. So you see nothing is here collected in the trash, but we can undo the last action if we just delete something and we don't like to have it deleted. We can go it back and get it back by this. Okay, that is these are the trash, the delete options. And now let's look into what we mean by, perhaps we make it larger here, so maximizing it, then we see a little bit more. So by the way, this hair cross here, the design node, we can also make it invisible. So then we don't are disturbed anymore. Okay, let's look in this option splitting. So eventually you might have the idea to split an element into pieces. So that would be just splitting into two pieces with the ratio of 0.5, that means 50%. Then it looks like this. So we just have split this element into two elements with the ratio of about just 1/2, one on the other element. So, and if we just would putting these elements back into one, that's exactly this merging option. So we select all these elements which we would like to merge into one, and also the intermediate nodes here. And after having done that, we just go to them with the mouse to one of these elements, right mouse, and we just go into merge. And you see, we have received back our one element. By the way, in the split option, if we just give an integer number, for instance 3, then this means the element would be split into 3 pieces of the same length. Again, making it back. We can also do it by undo last action. It's the same story. We can also give complete numbers here, calculating numbers. So if you would really divide the element into two parts with a ratio of 1/3, you can really type it in 1/3. about that to have exactly 1/3 and 2/3 split of this element. Again, we can merge these back into one element. That is the merging option. Then we have the blending option, but that is something which I would like to explain to you in the tutorial about generating cable nets in the context of form finding with force density. That would be a little bit too extensive here. So just refer to this tutorial. So much about elements, most important things, and looking forward to see you in the next tutorial. Thanks.